Somewhere in the universe, right now, an object exists that breaks every rule you've been taught about reality. Not bends the rules, breaks them. Physicists call it a black hole. But that word is almost too small for what it actually is. The one place where the two greatest theories humans have ever built, the physics of the impossibly large and the physics of the impossibly small, collide head-on. Here's the part that should be impossible. Nothing in this universe is supposed to vanish completely. Burn a letter, and the smoke and ash still contain, hidden somewhere in their chaos, every trace of what was written. Given enough time and computing power, you could, in theory, reconstruct it. This is one of the deepest laws in physics. Information can be scrambled, but it can never truly be destroyed. Now throw that letter into a black hole. Watch. Over trillions of years, that black hole slowly radiates itself away into nothing, shrinking, fading, evaporating. And when it's finally gone, so is your letter. Not hidden somewhere. Not scrambled into unreadable static. Erased completely, as if it had never existed. That should be impossible. Yet one of the most brilliant physicists in modern history proved that this might be exactly what happens. And in doing so, he set off a scientific war that has lasted 50 years and counting. So what really happens to information when a black hole dies? And what does the answer say about the fabric of reality itself? To understand why this question terrifies physicists, you need to know two rulebooks. The first is general relativity. Einstein's masterpiece describes gravity not as a force, but as the shape of space itself. Massive objects bending the fabric of the universe, everything else following the curve. This rulebook predicts black holes, regions where gravity grows so monstrous that space-time folds in on itself, crushing matter down into a singularity, a point of infinite density where the rulebook simply stops working. Push matter and energy past a certain point, and general relativity throws up its hands, refusing to predict anything further. It isn't just difficult to calculate what happens at a singularity. It's mathematically undefined, infinity itself, sitting at the center of a real physical object. The second is quantum mechanics, the physics of atoms and particles. Buried inside it is a sacred law called unitarity. Information, the complete data describing everything in the universe, can never be created or destroyed. It can be scrambled beyond recognition, hidden in impossibly complex patterns, but erased? Never. For most of the cosmos, these two rulebooks never have to fight. Gravity handles the stars. Quantum mechanics handles the atoms. They stay in their lanes. Black holes are not rare either. They sit at the heart of nearly every galaxy, including our own. Some are the collapsed corpses of dying stars. Others grew monstrous over billions of years, swallowing entire solar systems worth of matter, one bite at a time. They are some of the oldest, most powerful objects the universe has ever produced. Cosmic vaults sealed shut billions of years before humans existed to wonder about them. Except inside a black hole, where colossal gravity and quantum information are crushed into the same impossibly small space, and something has to give. For decades, this felt like an abstract puzzle, a curiosity for chalkboards, not reality. Then, in the 1970s, one physicist calculated what actually happens as a black hole grows old. What he found didn't just complicate the puzzle, it detonated it. For most of the 20th century, black holes lived up to their name. Perfect prisons, regions where gravity is so strong that not even light can climb back out. Cross the boundary, the event horizon, and you were gone. Forever, nothing escapes a black hole. That was the rule. Then, Stephen Hawking sat down with the equations of quantum mechanics and general relativity, expecting to confirm that rule. Instead, he broke it. Scientists weren't expecting this. Nobody was. Hawking discovered that black holes aren't perfectly black at all. At the very edge of the event horizon, the vacuum of space isn't as empty as it looks. Space, it turns out, is never truly still even in perfect emptiness. Quantum fields tremble with restless energy. spontaneously producing pairs of particles that appear from nothing and vanish just as fast. A kind of cosmic static running underneath everything. Even you, even this room, right now. But right at a black hole's boundary, something strange happens. One particle of the pair falls in. Its partner escapes outward into the universe as radiation. We call this Hawking radiation. And it means black holes are not eternal monsters. They die. At first, this felt like a triumph proof that gravity and quantum mechanics could be stitched together after all, even if only at the edges. They glow, faintly, almost imperceptibly, and with every particle that escapes, they lose a sliver of mass. Picture an ember burning so slowly it takes longer than the current age of the universe to finally go dark, flickering, endlessly, particle by particle, until one day, impossibly far in the future, it winks out completely. Trillions of years. That's not a typo. Trillions a span of time so vast that the entire history of Earth, from molten rock to right now, could repeat itself billions of times over before a single stellar mass black hole finished evaporating. This alone was extraordinary. But Hawking asked a harder question. What exactly is escaping? This is where the story turns dark. His calculations showed the radiation leaking out carries no fingerprints. It doesn't matter if you dropped in a star, a spaceship, or a diary. The radiation that escapes looks statistically identical every time, random, thermal, and utterly blank. Imagine burning every book ever written, every language, every secret, and no matter what you burned, the smoke always drifted out looking exactly the same. No trace of Shakespeare, no trace of your own diary, just uniform. Information, less haze. That's what Hawking's math predicted was happening to the universe's information. One evaporating black hole at a time. Physicists have a name for this transformation. A pure state, one containing complete, recoverable information, was somehow becoming a mixed state information soup, blended into nothing, permanently and irreversibly. For quantum mechanics, this wasn't just surprising, it was forbidden. Scientists tried to track the crisis using something called the page curve, a graph plotting how scrambled the escaping radiation should be over a black hole's life. If information truly survives, the graph should climb, then bend back down as the black hole nears the end, finally releasing what it's been hiding. But Hawking's version never bent down. It just kept climbing, all the way to the end, a graph shaped like a slow, silent scream. One faint glow. 1 trillion-year process. One question that would consume physics for the next 5 decades. Where did the information go? This single question ignited what historians of science now call the Black Hole War. On one side stood Stephen Hawking, defending his own math, insisting information really was destroyed, that black holes were the one place in the universe where quantum mechanics simply didn't apply. On the other side stood Leonard Susskind, a brilliant, stubborn physicist who refused to accept it. If Hawking was right, the most rigorously tested theory in the history of science would be wrong. To Susskind, that felt unthinkable. For almost 30 years, the argument raged across conferences, journals, and physics departments worldwide. But Susskind didn't just argue, he built an answer. Working from an idea first sparked by physicist Gerard Hooft, Susskind proposed something so strange it sounds like science fiction, the holographic principle. Picture every detail of a 3-dimensional room, every object, every shadow fully captured and stored on a flat, 2-dimensional surface, like the hologram on a credit card. Tilt it, and a 3D image leaps out at you, even though the actual data was stored completely flat. Susskind proposed that black holes work the same way. The information about everything that ever fell in isn't lost inside the black hole's volume. It's imprinted like a shadow onto its 2-dimensional surface, the event horizon itself. This wasn't just poetry. It had teeth. thanks to something called the Bekenstein bound, which proved a black hole's maximum information capacity scales with its surface area, not its volume. A black hole doesn't behave like a container at all. It behaves like a cosmic movie screen. Double a black hole's radius, and you don't just double how much it can store, you quadruple it, because surface area, not volume, is what counts. Scientists soon discovered something even stranger. This holographic idea wasn't just an elegant guess. It could be rigorously proven using a string theory framework called AD-S/CFT correspondence, showing that a gravitational universe and a flat, non-gravitational universe on its boundary could be two descriptions of the exact same reality, like translating one story into a completely different language and losing nothing. The evidence mounted for years. And in 2004, Stephen Hawking did something almost unheard of in science. He admitted he was wrong. Information, he conceded, survives. It escapes. The universe does not forget. But this is only the beginning. Because holography wasn't the only battlefield. While Susskind reshaped black holes into cosmic hard drives, another group of physicists attacked the problem from a wildly different angle. What if a black hole never actually forms a singularity at all? This is the world of loop quantum gravity, built on the mind-bending idea that space-time itself is not smooth. It's grainy, made of discrete, indivisible units, like pixels on the universe's screen, far too small for any instrument to have ever seen directly. If space-time truly is pixelated at this scale, it can never be crushed into an infinitely small point. There's a floor, a limit. And when collapsing matter hits that floor, it doesn't vanish into a singularity. It bounces. Picture matter falling forever, faster and faster, expecting to be crushed into nothingness, only to slam into an invisible, unbreakable floor and rebound outward violently, like a spring compressed past its limit. This quantum bounce leads to two of the most audacious ideas in modern physics. In the first, the white hole shockwave model. The bounce sends a shockwave rippling outward through the collapsing star. That shockwave eventually catches the event horizon itself, and the entire black hole structure disappears, releasing everything all at once, well before the dreaded page time ever arrives. The paradox never even gets the chance to happen. In the second, stranger still, the black hole evaporates almost exactly as Hawking predicted, shrinking down to the smallest conceivable scale, the Planck scale, before quantum tunneling flips it inside out into an anti-black hole, a white hole. Here's the twist. Inside, the black hole's interior volume doesn't stay small. It grows immensely, far beyond what its outer surface would ever suggest. The inside becomes gigantic compared to the outside. Enough room, physicists argue, to safely store every scrap of information that ever fell in until the white hole finally lets it go. Two battlefields, two solutions, and physics still wasn't finished being strange. Just when it seemed holography had rescued the universe, physicists found something even more unsettling, hiding inside their own solution. In 2012, researchers uncovered a paradox within the paradox, the monogamy of entanglement. For radiation to carry information out of a black hole, each escaping particle needs to be quantum entangled, mysteriously linked with radiation that already escaped earlier. But standard quantum theory also demands that same particle stay entangled with its twin, the partner particle that fell inward. Here's the impossible part. A single particle cannot be fully entangled with two separate things at once. It's like being someone's identical twin, completely, perfectly bonded to two different people simultaneously. The universe doesn't allow it. Something had to break. To resolve it, physicists proposed one of the most terrifying ideas in modern physics, the AMP's firewall. If a particle's bond with its infalling twin has to be severed to preserve information, that break wouldn't be silent. It would release a catastrophic burst of energy right at the event horizon, a wall of pure, incinerating radiation. For over 100 years, physicists had promised that a falling observer would notice nothing unusual at the horizon, no dramatic sign, no wall, nothing marking the point of no return. The firewall proposal shattered that promise completely. Any astronaut crossing the horizon would be vaporized instantly, burned to nothing the moment they arrived. This forced physicists into an agonizing choice: save quantum mechanics and shatter Einstein's cherished equivalence principle, the idea that falling through a horizon should feel like nothing special at all, or protect Einstein and let information die after all. Two of modern physics' greatest achievements suddenly pointed like loaded guns at each other. Then, Juan Maldacena and Leonard Susskind proposed something almost too strange to believe. ER_EPR. What if the entangled particles, the one falling in and its twin escaping outward, were never separate at all? What if they're connected by an actual, physical structure, a microscopic wormhole threading invisibly through space-time? If true, entanglement and wormholes might be the same phenomenon wearing two different disguises. The firewall dissolves, because there was never a monogamy violation to begin with. Space-time itself, Maldacena and Susskind suggested, might be woven directly out of quantum entanglement. But the most staggering idea of all is newer still, and far stranger. What if black holes never fully die? A radical new framework, built from a higher dimensional theory called Einstein-Cartan gravity, suggests black holes don't evaporate down to nothing. They leave something behind, a remnant. Not a remnant the size of a mountain, or a marble, or even a grain of sand. A remnant so small it makes a single proton look colossal, by comparison a scrap of mass so faint that no instrument humanity has ever built could hope to detect it directly. Yet according to the math, remnants like this could be scattered across the universe right now, tucked inside the aftermath of ancient, long-dead black holes, quietly holding on to secrets from the dawn of time. This theory proposes that at the deepest, smallest scale of reality, space-time doesn't just bend. It twists a property called torsion, and at extreme densities, that twisting acts like a repulsive force, powerful enough to halt a black hole's collapse completely. What's left is a tiny, silent vault, frozen at the very edge of existence, storing the black hole's information forever inside delicate, long-lived vibrations of space-time itself. And here's the detail that turns this from strange to almost unbelievable. When scientists mathematically shrink this seven-dimensional framework down into the 4 dimensions we actually live in, something astonishing falls out of the equations. The Higgs field, the very mechanism that gives particles mass. The same theory that might explain how black holes secretly preserve the universe's deepest secrets might also explain why anything has mass at all. So what does it mean, really, that black holes might not destroy anything at all? It means the universe, at its core, might be obsessively, almost stubbornly committed to memory. Every particle that has ever existed, every collision, every collapse, every ancient star that burned out into darkness. According to the physics unfolding right now, none of it may ever be fully erased, only transformed, scrambled, hidden in patterns so complex that recovering them would take almost the entire lifespan of the cosmos. There's something strangely comforting in that. We spend our whole lives afraid of endings, of being forgotten. And yet the deepest laws of physics, the ones we're only now beginning to decode, suggest that information, in some fundamental sense, cannot truly disappear. Not even inside the most violent, devouring objects the universe has ever built. Black holes were once symbols of total annihilation, cosmic mouths swallowing everything, including light, and giving nothing back. Today, they might be something closer to the opposite, the universe's most extreme filing cabinets, compressing entire histories down onto surfaces, into wormholes, or into microscopic seeds smaller than an atom's shadow. We still don't have the final answer. Holography, loop quantum gravity, Firewalls, wormholes, seven-dimensional remnants. These are competing chapters in a story physics hasn't finished writing. But every one of these ideas is reaching for the exact same thing. A single theory of quantum gravity. One set of rules that finally unites the impossibly large with the impossibly small. That theory might be decades away, or it might be one insight away, waiting for someone alive right now to find it. Perhaps it will come from a university lab, perhaps from a stray idea scribbled on a napkin. Physics has a habit of rewarding exactly that kind of curiosity. Because black holes were never really about black holes. They are the universe daring us to ask what reality is actually made of. And somewhere, at the edge of a silent, dying star, space-time is still keeping score, refusing, against every impossible odd, to let a single piece of the universe's story ever truly be forgotten.